Greetings everyone, and today we are going to discuss about electric flux. So, for electric flux, suppose a small element of vector area A, small element of vector area A is placed in the electric field. Suppose a small element of vector area A is placed in the electric field. Small element of vector area A is placed in the electric field. Now, in this case, as the small element of vector area is placed in an electric field, electric flux can be defined as the total number of electric field lines of force passing through a small element of vector area A. In this case, the total number of electric field lines of force passing through a small element of vector area A is known as electric flux. More the number of electric field lines passing through the small element of vector area A, more stronger the electric flux is. And dot product of electric field intensity and a small element of vector area A can be considered to be electric flux. And dot product is always a scalar. Dot product is there, and as it is dot product, it is a scalar quantity. Scalar. Apart from which, E dot A is the dot product of electric field intensity and small element of vector area. E dot A is the dot product, whereas E A cos theta is the magnitude of electric flux. Ea cos theta is the magnitude of electric flux. Now in this case, if theta is equal to 0, then the electric flux is maximum. If theta is equals to 90, electric flux is 0. If theta is equals to 180, electric flux is negative. If theta is equals to 270, electric flux is 0. If theta is equals to 360, electric flux is maximum. In this case, we are only deriving the trigonometric ratios. Cos 0 is equals to 1, cos 180 is equals to minus 1, cos 90 is equals to 0, cos 270 is 0. In that case, if theta is greater than 0, then the electric flux will be done in the first quadrant. As it is done in the first quadrant, the electric flux will be positive. After which, if theta is greater than 90, electric flux is negative in the second quadrant. If theta is greater than 180, then electric flux is negative in the third quadrant. If theta is greater than 270 or theta is less than 0, then the electric flux produced will be positive in the fourth quadrant, which means in first and fourth quadrant it is positive, and in the second and third quadrant it's negative. Now in that case, uh, if theta is equals to 268, electric flux is negative in the third quadrant, right? After which, there is an exceptional case here, that as we know, the electric field lines of force are perpendicular to each other. As these electric field lines of force are perpendicular to each other, we can say that when these electric field lines of force are perpendicular to each other, if the surface, small element of vector area A, is kept straight, if this small element of vector area A is kept perpendicular to the electric field lines of force, which are themselves perpendicular as well, then the electric flux produced will be maximum, due to which whenever these both of these are kept perpendicular to each other, then the electric flux will be maximum. Electric flux should have a condition: electric field lines of force are perpendicular already, and the small element of vector area A should be perpendicular as well. In that case, both are perpendicular, and thus as both are perpendicular, they are parallel to each other, due to which the force is Ea or maximum. Similarly, if it is tilted a bit, then it depends on the angle which it forms, which is theta, which is equal to dot product of E dot A, where whatever the value of theta is, the answer will be given. After which, if you are putting the small element of vector area I perpendicular, if you are putting the small element of vector area I parallel, for suppose this is small element of vector area's direction, and as the electric field lines of force are perpendicular to each other, then the angle formed would be 90, and in that case, the when the small element of vector area is parallel, the electric flux will be 0. Now, coming to a short derivation, suppose an isolated positive point charge q is situated at the center of a sphere of radius r. Now, in that case, We previously have been known that electric field intensity is equal to kq upon r square, uh, unit vector r, where r hat is a unit vector directed from O to P. One more thing I would like to discuss here about the dimension of electric field intensity. Dimension of electric field intensity can be defined in such a manner that this is mlt minus 2. This is the dimension of force, mlt minus force upon q naught per unit charge or per positive test charge q naught, which is a 80. Now in this case, answer will be in such a manner that m l t minus 3, a minus 1 is the dimension of mlt minus 3, a minus 1 is the dimension of electric field intensity. Now accordingly, this was a thing remaining to be discussed. And here, when we're going to put the value of electric field intensity over here, and we know that the area of the particular point charge is equal to 4 pi r square. Now when we're going to put both the values, when we're going to manipulate it, answer will become as 4 cancel with 4, pi cancel, r square cancel, with 4 pi r square, due to which q upon epsilon naught is the equation, which is the equation which shows that the electric flux present in an enclosed charge, the electric flux in an enclosed shape, an electric flux in an enclosed shape is 1 upon epsilon naught times the charge present in that closed shape. So in that case, this condition was given by scientist named as Gauss, and that is known as Gauss law. And in that case, he described that the electric flux experienced by an enclosed shape is 1 upon epsilon naught times the charge present in that closed shape. And that's Gauss law is applicable on any shape. It should not be particularly sphere, it can be rectangle, square, oval, parallelogram, whatever the shape is. So in that case, this is a brief explanation. Hopefully you enjoyed the video. We'll meet again in another one.